I welcome you all in this course on steam and gas power systems. In this session, we will solve a few problems based on this course starting from steam power system. So, first problem is related with the steam power system based on Rankine cycle, modified Rankine cycle. In a steam power plant, working on Rankine cycle, steam enters the HP turbine at 30 bar and pressure 400 degree centigrade. So, there is a steam power plant. In this power plant, we will draw the processes on temperature entropy diagram. This is quality 0, this is quality 1. The steam enters the HP turbine at 30 bar pressure and 400 degree centigrade temperature. So, 30 bar 400 degree centigrade the steam enters the turbine, right. So, P1 is 30 bar and T1 is 400 degree centigrade. The steam expands in HP turbine up to 6 bar pressure and then is reheated to 400 degree centigrade again. So, that temperature is restored in a reheater. From the reheater, the steam enters the low pressure turbine and expands to 0.1 bar pressure. The isentropic efficiency of both the turbines is 0.8. Isentropic efficiency of both the turbines is 0.8. Now, the issue is this definitely, first of all, let us find out the state of steam at 30 bar pressure and 400 degree centigrade temperature. So, if we look at this steam table, this is 30 bar is 3 megapascal. So, at 3 megapascal pressure, the saturation temperature is 233.85 degree centigrade. It means the steam is superheated. Now, superheated steam at 400 degree centigrade, the enthalpy of the steam is 2933.5. This is internal energy, sorry, enthalpy is 3231.7 kilojoules per kg, right. So, H1 is 3231.7 kilojoules per kg and T1 is already given. So, it is a superheated steam. Now, entropy, because the expansion is isentropic process. The entropy at this stage is 406.9234, 6.9234 kilojoules per kg Kelvin, right. So, we have state fix. Now, isentropic expansion is taking place up to 6 bar, state 2, 6 bar. So, at 6 bar entropy is going to remain constant. So, let us look at the properties at 6 bar, that is 6 kilopascal. The entropy, constant entropy. So, when the entropy is remaining constant, it is saturated vapor, the entropy is 6.7592. It means at 6 bar the steam is still superheated, right, and through cross interpretation because at 400 degree centigrade it is 7.7. So, 6.92 will lie between these two, 200 degree and 158 degree. So, linear interpolation will be done and then we will get the value of S2 is equal to 6.9233 is equal to SF plus X SFG, right. A similar type of numericals we have solved similar type of numericals with the respective lecture related with the vapor power cycles. From here we will get the value of X, right. Now, H2 I have done the cross interpretation. Now, H2 is 2830.3 kilojoules per kg. right? And X we cannot calculate because this is already superheated. So, this cannot be done. So, vapor is superheated at state 1, it is expanded to state 2, right? At state 2 it appears to be superheated, and it is superheated because the entropy is 6.7592 and here entropy is 6.9232. So, it is superheated, and through linear interpolation we have calculated the value of H2S. So, H1 is 3231.7 and H2 is 2830.3 kilojoules per kg Kelvin, But this is not an isentropic process. In actual, it is process is like this. This is 2 dash, right? And it is falling on this line. So, H2 dash, then again H2 dash minus H1 divided by H2 minus, sorry, H1 minus H2 dash divided by H1 minus H2 is equal to efficiency, isentropic efficiency of turbine. It is already given. So, it is isentropic efficiency is already given. We have the values of H1 and H2 as well. So, H2 dash can be calculated from here, and H2 dash is 2910.9 kilojoules per kg. Now, this superheated vapor is reheated up to state 3, and that is again at 400 degrees centigrade. So, T3 is 400 degrees centigrade. So, from here the properties of superheated vapor at 400 degrees centigrade we can get the value of enthalpy. So, H3 is 3270.8. kilojoules per kg. This is enthalpy at state 3. Now, again steam is expanding and it is going up to 0.1 bar. Now, entropy at state 3 S3 is, it is 600 kilopascal, 400, it is 7.7097 kilojoules per kg. Now, entropy of at 0.1 bar, this is 10 kilopascal, the entropy is 8.1488. It means the vapor is, the quality of vapor is less than 1. So, we will take S3 is equal to, this is, let us say this is 4, SF4 plus X S FG4. Now, entropy starting from here, entropy at state 3 is equal to entropy at state 4, because saturated vapor, the entropy of saturated vapor at state 4 is higher than the entropy at state 3. That is why the vapor available at state 4 is does not have quality is equal to 1, it is quality less than 1. So, I am repeating the steps. First of all, we have taken the steam, superheated steam at state 1, properties are taken from the steam table at 400 degree centigrade temperature and 30 bar. Steam is expanded to 6 bar. We have compared the properties and we have found that at 6 bar also or 600 kilopascal also the steam is superheated, right. By linear interpolation from the steam table we have calculated the enthalpy at state 2. Efficiency is given, we have calculated the enthalpy at state 2 dash because efficiency is 0.9. Then again it is reheated to state 3 which is at 400 degree centigrade. So, those properties are also taken from the steam table for the superheated vapor at 600 kilopascal. Then steam is expanded in the low pressure turbine, and at the exit the pressure is 0.1 bar, and now we have compared the entropies. We have found that the quality is less than 1. So, we are going to use this equation. Now, S3 we have taken from here, SF4 and SFG4, S4 and SFG4 shall be taken from the steam table, and after manipulation the value of quality is 0.94. So, X is equal to 0.94. That is the quality of vapor at this state. Once we have the quality of vapor at this state, then we can find the H4 as HF4 plus X HFG4, right? And using this equation, when we calculate the value of H4, then we get the value of H4 as 2440.4 kilojoules per kg. But this process is also not isentropic, right? So, we get another state four dash, this is 4, right? And for 4 dash, again isentropic efficiency is H3 minus H4 dash divided by H3 minus H4. Now, from here we get the enthalpy at 4 dash. So, H4 dash is 2606 2606.5 kilojoules per kg, right? Now, we have enthalpies at all the salient points. Now, this vapor is then available at the exit of the turbine. It is condensed, fully condensed, then we get 5, then pressurized, and then it goes to the boiler, and then like this. So, it is 5, 6, 7 and then 1, this is 8 and then 1. So, feed water goes to the boiler at pressure 6, at state 6, heat is added here up to state 1, expansion in high pressure turbine, then again reheat, and then expansion in low pressure turbine, and then condensation in condenser. Now, work of the pump is equal to specific volume of the pump, specific volume specific volume at state 5, state volume, and P6 minus P5. P5 is 0.1 bar, P6 is 30 bar. So, it is 101 into 10 to power minus 5 and 30 minus 0.1 into 10 to power 2. Then that is in kilojoules of per kg input given by the pump, that is VDP. So, because this is given in bar, we have converted into the kilojoules, kilopascal. This pressure in bar is converted into the pressure in kilopascal, and then we have calculated the work of the pump. Now, work of the turbine is equal to H1 minus H2 dash plus H3 minus H4 dash. This is because we are getting work output from here and work output from here. Net output is because part of this energy is used for running the pump. So, this will be minus work of the pump will be the net output of from the system, from the cycle. Output of the turbines minus energy consumed by the pump. Now heat supplied. Now heat supplied during this process is equal to, now we do not know the enthalpy at state 6, but we have enthalpy of state 5, that is enthalpy of saturated liquid at 0.15 bar, that is HF 191.81. So if in this enthalpy we add the pump work, we will get enthalpy of state 6, or what we can do, H1 minus H5, that is enthalpy difference between this and this, and we will add the pump work. Then we will get enthalpy at state 6, because now after calculating the net output, we have to calculate how much heat is given in the system. So heat is given in the cycle is H1 minus H6, but we do not have the enthalpy at H6 because H6 fluid is compressed liquid, right, but we have enthalpy at state 5. This enthalpy at state 5 is nothing but the enthalpy of the liquid HF 191.81. Okay. So heat added during this process H6 to H1, we can take H1 minus H5, this is enthalpy this minus enthalpy this plus, sorry, minus work consumed by the pump, because this is not, this energy is not added in the boilers. So minus work of the pump. So that is the net heat added from state 1 to state 6 plus heat added during state 3 to state 2 dash, because it is a reheat cycle, plus H3 minus H2 dash. This is the net amount of heat added in this cycle. So here in this question we have to find the net output per kg of steam mass flow rate. So net output we are getting from here, from this equation, all the values are known to us, right. Thermal efficiency of the cycle, we will take the ratio, net output divided by the heat supplied will give the thermal efficiency of the cycle. Now the third one is steam rate. Steam rate is 3600 divided by W, that is the output, and this will be in kg per kilowatt hour, right. And next is Carnot efficiency for the temperature limits of the reheat cycle. So Carnot efficiency, the minimum temperature is this, maximum temperature is this. So we can always calculate the Carnot efficiency of the cycle, right. Now after this we will take another numerical on gas turbines. Now we will quickly go through the steps to solve this numerical. Now this numerical has two-stage compression. It is, the gas turbine is equipped with intercooling, regeneration and reheat arrangements. Okay. So a gas turbine is equipped with intercooling, regeneration and reheat arrangement. The HP turbine is used to drive the compressor and LV turbine gives the output. So there are two turbines, one is driving the compressor and another is giving the output. The exhaust pressure of LP turbine is 1 bar and the turbine inlet temperature for both the turbine is 1020 Kelvin. The isentropic efficiency of turbine and compressors is 0.85. The compression takes place in two stages. So there are two compressors. So there are two compressors and two turbines, right. The atmospheric temperature and pressure are 300 Kelvin and 1 bar respectively. The effectiveness of regeneration is 75%. Consider the air as the working fluid throughout the cycle. Find the following: output of the cycle, thermal efficiency, specific air consumption in kg per kilowatt hour. So, it is a cycle which is drawn on temperature entropy diagram. It has two stage compression. It is so 1 to 2 and it has certain isentropic efficiency 2 dash, then cooling. After cooling again it is 3 and then this is 3 dash. So, first compression and then intercooling and then again compression. Then in the combustion chamber there are two turbines. So, state है हाँ वो मैं इसमें दिखाई नहीं दे रहा ना इसलिए बोल रहा हूँ ठीक T6 and then expansion is high pressure turbine, then we get T6 to 7 state 7 to then again state this temperature at 6 is equal to temperature at 8, then again expansion and we get state 9 and this is 9 dash. So, compression then cooling, because there is a perfect intercooling, then T1 is equal to T3 and then heat addition, expansion in turbine and then again reheating and T6 is equal to T8. It is given in the problem statement, then expansion in high pressure turbine and low pressure turbine. This is the arrangement. Now, here again first of all we will calculate the value of T2. T2 is equal to T1 raised to power P2 by P1 raised to power T1 multiplied by P2 by P1 raised to power gamma minus 1 over gamma. Now, T1 is 300 and P2 is 2.5. Pressure ratio in each compression stage is 2.5 raised to power 0.286 and this will give as 389.8 Kelvin. So, T2 is 389.8 Kelvin, right. Now, similarly, we will calculate the T2 dash and in order to calculate T2 dash again the efficiency is equal to T2 minus T1 divided by T2 dash minus T1. Here we have the value of T2 and T1 as well and efficiency is also with us, right. So, we using these values we will get the T2 dash as 405.6 Kelvin. Now, we need not calculate the value of T3 and T3 dash because T2 dash is going to be, because polytropic efficiency is same. So, T2 dash is equal to T3 dash and T1 is equal to T3. So, T3 dash is also equal to T2 dash. Okay. Sorry, this is not 3, this is 3, this is 4. This is not 3, this is 4. This is 4 dash. So, T4 dash. So, we need not calculate the value of 4 or 4 dash. So, T4 is equal to T2 and T4 dash is equal to T2 dash. Now, work of the compressor is equal to first Cp T2 dash minus T1, because there is perfect intercooling, work in both the work consumed by both the compressor is same. So, we can always multiply it by 2. T2 dash and T1, when we are putting the values, we are getting the work of the compressor as 212.3 kilojoules per kg. Now, the work of compressor with us. Now, these compressors are run with the high pressure turbine as per the statement of the problem. The HP turbine is used to drive compressors and LP turbine gives the output. It means Cp T6 minus T7 is equal to 212.3, right, and T6 we have with us 1020, T6 is 1020 Kelvin. So, T6 is with us, we can calculate the value of T7 and T7 is, sorry, here there is a correction, instead of T6 it is T7 dash, because the power is developed in this process, so it is going to be T7 dash, right. So, Cp T6 minus T7 dash, now from here we will get the value of T7 dash. Once, and that is equal to 808.8 Kelvin. Now, once we have the value of T7 dash, we can calculate the value of T7. It is T6 minus T7 dash divided by T6 minus T7. Efficiency of the turbine is 0.85. T6 is, we have already, it is given in the problem statement. T7 dash we have calculated right now. Now we can calculate the value of T7. Now the T7 is 771.1 Kelvin. Sorry, it's 701.5 Kelvin. We have already, we are having the value of T7, we are having the value of T6, we are also having the value of P6. Now we can get the value of P7. So T6 by T7 is equal to P6 by P7 raised to power gamma minus 1 over gamma. From here we will get the value of P7. Now the P7 is 2.35 bar, right. Now P7 is same as P8, it is a constant pressure process. Now we have the value of T8 and P8, now we can find the value of T9. T9 is equal to T8 1 by exhaust pressure is 1 bar. So 1 by or we can write P9 by P8 raised to power gamma minus 1 over gamma. So this is 1 bar and T8 is 1020, 1 by P8, P8 is P7 2.35, 0.286, and this will give the value of temperature at state 9, and this is 799.1 Kelvin. Again we have the efficiency of this 0.85 and we can calculate the value of T9 dash, and T9 dash is 872.2 Kelvin, right. Now we have temperatures at all salient states or salient points. Now work of the turbine is equal to Cp T8 minus T9 dash during this process. Cp for air we know, that is 1.005, 1020 minus 832.2, and this work of the turbine is equal to 188.7 kilojoules per kg, right. Now with the exhaust of this, heating of the gas which is coming from the compressor is done, right. So gas available is at T9 dash and compressor outlet is T4 dash, and suppose it is heated up to T5, right. So actual heat transfer is T5 minus T4 dash multiplied by Cp divided by maximum possible heat transfer, that is T9 dash minus T4 dash into Cp, and that is equal to how much? Effectiveness is 75%, 0.75. Now from here we will get the value of T5, because T4 dash is with us, T9 we have already calculated, T4 dash Cp will be cancelled, 0.75 is given. So From here we will get the value of T5, and T5 is 725.5 Kelvin, right. Now heat added in the cycle. Now heat added is Q. Now heat added is enthalpy at 6 minus enthalpy at 5. So Q is Cp T6 minus T5 plus Cp T8 minus T7 dash. We have temperatures at all these points. Cp we can take for air, and now we get the value of Q is 508.1 kilojoules per kg, because in the entire cycle heat is added at two places, here and here, and this much heat is coming from the exhaust gases, right. Now we have the value of Q. Thermal efficiency is going to be the output of this turbine divided by Q, because this output of this turbine is used to run the compressor. So it is going to be 188.7 divided by 508.1 into 100, and this is going to be 37.1%. And specific air consumption is nothing but 3600 divided by work of the turbine 188.7, and that is going to be equal to 19.08 kg per kilowatt hour. Now after this we will quickly go for this numerical. This is very interesting numericals on the leakage in or losses in steam turbines. In this numerical, it is stated that they calculate the leakage loss through diaphragm packing in a turbine under the following condition: steam pressure before nozzle, steam. So we have to calculate the leakage through the diaphragm. In the diaphragm, the nozzles are fixed. The steam pressure before nozzle 14 bar, steam superheat 55 degrees centigrade, steam pressure after nozzle is given, shaft diameter is given, radial clearance. So the leakage will take place through radial clearance, right? And there are constrictions. I will draw a larger figure. There are constrictions provided here, and number of constrictions is 4. So 4 constrictions are provided. So it means dwell spaces are 3. This side pressure is 14 bar. Now we have to calculate how much steam will leak through the constrictions. Clearance is also given here. Radial clearance is 0.04 centimeters. It is around 400 microns, right. So first of all, from steam table, Ts corresponding saturation temperature corresponding to 14 bar. So Ts is equal to 195.04 degrees centigrade. This is the saturation temperature from steam table, but the steam is superheated by 55 degrees centigrade. So degree of superheat, this is 55 degrees centigrade is degree of superheat. So we will add 55 here. So temperature of the steam is 250.04 degrees centigrade. Now area of constriction Ag. Now Ag is Cc pi d, and this is clearance, right. This is constriction coefficient, because when there is a flow in sudden obstruction or sudden contraction or enlargement, vena contracta is formed. So that has been taken account here in Cc. right. So, it is 0. Coefficient of contraction 0.75 into pi into diameter is 250 mm. So, it is 0.25 into 0.04 into 10 to power minus 2, and that is the area, right. And this is AG is, we will write here, AG is 2.355 into 10 to power minus 4 meter square. Second thing we have to see, on the trailing side, the pressure is greater than critical pressure or less than critical pressure, because in both the cases the analysis will be different. So, on this side, trailing side, the critical pressure is 0.85 P1 under root ZC plus 1.5. Here ZC is number of constriction, there are 4, and P1 is 14 bar, right. And now from here we get the P critical as 5.074 bar. Now, this critical pressure is less than the pressure on that side, it is 12.5 bar. It means on the other side the pressure is not less than the critical pressure, it is above the critical pressure. When on the other side, when the pressure is above the critical pressure, the leakage through the constriction will be mass leak is going to be AG under root P1 square minus P2 square divided by Z P1 V1. Now, we have the value of P1 14 bar, P2 how much 12.5 bar, we will convert them into kilopascal, right, and then Z P1, this is P1 same, Z P1 and specific volume. So, specific volume of steam, superheated steam, we have taken from the steam table as 0.1635 meter cube per kg. So, initially we had a steam which is superheated by 55 degree centigrade. So, we have taken the specific volume of that steam, right, from the steam table, that is this specific volume. Initial pressure is known, that is 14 bar, and pressure on the other side is 12.5 bar, and this will give the leakage as mass of the leakage as 0.155 kg per second. So, this is the leakage, this is the amount of leakage which is taking place through these constrictions. Now, it has 3 dwells, and dwell spaces, number of dwell spaces is 3, and M is also equal to AG under root P1 square minus Px square divided by ZC P1 V1. ठीक है. Now, here leakage is, because it is moving in this direction, so leakage is same 0.155. P1 is 14 bar, this is 14 bar, right. Now, ZC we have to see, now P1 is again 14 bar, Px we have to calculate, I think also calculate the pressures in the dwell spaces. So, dwell space, pressure in dwell space 1, pressure in dwell space 2, pressure in dwell space 3. So, this we have to calculate, rest of the information is with us, and if we put the values, we get the value for Px as under root 196 minus 9.915 ZC. When we put ZC is equal to 1, we get the value of Px right here. When Zc is equal to 1, then, or we can say P1 is equal to 13.64. When we put this is equal to 2, then we get P2 is equal to 13.27, and when we put this is equal to 3, we get P3 as 12.98 bar. They are all bar, right? And beyond that, there is a pressure of 12.5 bar. So this is how we can calculate. Because this information helps in designing the seals for steam turbines. Okay, this was the last lecture. I wish all of you best of luck for the coming examination of this course. Thank you very much.